while we're waiting, as a precursor, Roland was telling me he has not only one of the keyboards that he's did testing on, he has 3. So he's very passionate about this keyboard that we're going to be showing some testing on.
Contains very dirty code in the firmware, but makes a great Christmas gift.
There we go. Okay, let's go ahead and just get started with today's session. So thank you for the folks joining, wherever you're watching from. Today's session on Code Unboxed with TrustInSoft is about Keychron. Before we do get started and get into the analysis that's been performed by Roland, I do want to just talk about a few housekeeping items and then also our vulnerability disclosure policy. So this session is being recorded and will be made available for on-demand viewing. We do follow with all of these Code Unboxed events, we do follow a 90-day disclosure policy where 90 days prior to the event, so specifically today's event, we would notify the owner of the respective code that we're going to be showing analysis on for any of the bugs or vulnerabilities that we have identified, giving them the opportunity to address any of the issues identified. So we're pretty strict at that, and we do follow that 90-day disclosure policy. On that note, as I had mentioned today, Roland Dudumain will be showing the analysis that he has performed and talking through some of his findings. As I mentioned earlier, we will be focusing specifically on the Keychron keyboard. Roland has many of them. I will let Roland talk a little bit about the Keychron keyboard and a little bit more about it. So Roland, over to you.
Thank you. So the Keychron keyboard it's a mechanical keyboard like many hacking engineers love to have. So that one is great because I use it for travel. What's interesting for TrustInSoft is that it's not only is it actually good for typing code or analysis in drivers and so on, but also it's a good representative firmware or IoT system that has an STM32, a small microcontroller with a lot of IOs. When you check out the source code, and I'll mention that later on, it's a sizable piece of code. And even when you build it, you end up with about 170 files, almost 170 files that are considered in the active build. So that's actually quite nice because you can see how an analysis of a sizable piece of code can be achieved with our formal analysis tools. Well, in case you were wondering if I found something, then the answer is yes.
Thank you, Roland. So before we get into it, if you're not aware of who TrustInSoft is and what we do, let me just talk through at a very high level quickly what TrustInSoft does and some of the problems that we do solve for. So specifically, one of our missions is to empower developers to deliver mathematically proven zero defect products. Now, that's an extremely broad goal and mission in life, and it's definitely what we at TrustInSoft do focus on, providing tooling to help developers deliver mathematically proven zero defect products. So how do we do it? First and foremost, we do have a solution called TrustInSoft Analyzer, which specifically focuses on utilizing formal methods. If you're not aware of what formal methods does, we are able to mathematically, by using formal methods and abstract interpretation, mathematically prove that the code that we have analyzed, if there are 0 bugs, there are 0 bugs. But we're able to mathematically prove and verify and validate that it is bug-free for the respective code that we've analyzed. In addition to that, we can and we do, through generalized inputs, we're able to inspect and analyze and perform exhaustive testing, where one might have to typically create many unit tests, right? So instead of writing and creating many unit tests, just via a generalized input, we can test and validate hundreds of unit tests, often thousands of unit tests that you typically wouldn't have to write yourself. And then from a depth of analysis, kind of related to the benefit of using formal methods, we're able to find 100% of the flaws and vulnerabilities just based off the utilization of formal methods. So what does that mean? When you look at real world, I suppose, comparison and of typical static analysis solutions, when you're performing static analysis, you can and often do miss some paths in the respective code base. Here's some examples of some well-known issues in the world that have happened. One was Heartbleed, which was an OpenSSL vulnerability as a result of improper input validation. Another one was, if you haven't heard about it, the CrowdStrike outage earlier this year, where that resulted in, frankly, billions of dollars of impact. And that was as a result of an invalid memory read. And then a little bit of an older example is Ariane flight, a rocket explosion, which costed hundreds of millions of dollars as well. And that was a result of integer overflow issues. So Roland's going to get into much more details from a technical perspective on this, but when you're utilizing formal methods, and specifically you're able to perform exhaustive static analysis, as you see in the visual representation there, that gives you the ability to inspect and evaluate and ensure that you're not missing any code paths. So that's that exhaustive component that TrustInSoft offers as a result of utilizing formal methods. So with that, let me hand over to Roland just to talk a little bit about the analysis that he's going to be doing and showing that he has done. And then Roland, over to you.
Yep. So in the previous Code Unboxed sessions that we did, actually no, the previous one I did was similar, but the first one that we did that Clément did were actually focusing on verifying an API or a set of functions. Here it's going to start from the entry point of the firmware and actually verify the integrated image. So what's going to be interesting in this, and you'll see it when I do it over there in the coming minutes, is that it's going to model everything that the chip is doing. Okay, so when we start to do some preparation, the demo itself is going to focus on the tool, but before being able to build the tool, and that's the last line that you see here, I'll get to it in a minute. You'll see that well, you really have to check out a few things, to install a few tools. There's that QMK tool, and then well, at some point you can start to really build. So let me share my screen now. Okay, starting from the web page of the Keychron QMK firmware, here we have the command to build it. I don't have the ANSI keyboard, I have the ISO keyboard, so here I'll just use the ISO command instead. Switching to VS Code here, let me start the bare command on that command with ISO here, which is otherwise the same. And it's building, taking a little bit of time, and then building all the files here. At the end of that, we should have compile commands. This is taking a little bit of time because there are about 170 files. We can look at the structure here. For example, here inside lib, we have the small ChibOS, and then the platforms where the QMK keyboard firmware actually supports AVR, and ARM in our case will be on ARM. On 32-bit. There's a huge amount of keyboards supported, but in this particular branch, which is the Keychron branch, it's only Keychron, and in case you didn't know, OnePlus as well. Okay, so the compilation has finished. We can see that we have a compile command now, which we'll focus on in a second. But at least we can create a first project for this analyzer. Here in the configuration file, we can start to clean up all the commands here. Actually, let me do it in a forceful way, because that's going to be the easiest way, like this. Oh, some spaces. Okay, let me remove that by hand. That's please simpler. And then let's point to the compilation database that we just did. It's actually not in TrustInSoft, it's one level up. We need to also describe the architecture, the MacDeb. In our case, as I mentioned, this is the ARM 32-bit platform, Army ABI, with some GCC extensions. But yeah, as we'll see, there are more issues to come regarding GCC compatibility, because many extensions are used in this particular one. We need to define the files here. So to look at the files, the trick can be a simple grep command to grep files inside the compile commands and then copy the list here. We are copying the full list of all the files that were built, but of course what we want to exclude are the assembly files, because this analyzer only starts from C source and C++ and soon more. Okay, let's remove that, and then let's search for .s, capital S, like this. Now we end up on these. Yeah, sorry. I wanted to first remove all the files, and then I'll remove all the assembly files. Okay. And now we had some assembly files here. All right, so at least the project is ready. Now we can start parsing. I guess it won't work on the first run, but let's see. And well, as expected, the first issue here is about thumb interworking. Well, if you don't know the ARM architecture, they have kind of 2 or 3 encoding for the instructions. One is the ARM 32-bit full instructions, 4 bytes. Then there's the thumb, and then most recent cores, including the one in my keyboard, actually are using always thumb. So the interworking is actually not something that's necessary, and we can just remove it. In fact, I searched online, and looking at the definition in the GCC manual, it says that the default is no thumb interwork. So it's a little bit pointless to actually keep it. So let's search for it. We find it here in a few places, and I don't know why, but it's not in the compilation database. But let's remove it everywhere. Yes. I'll also open the compile commands, and in here, I'm also going to remove that everywhere from the file. Okay, let's try again. It goes much further now. There is still one compiler optimization disabled, which I don't know what happens, but all right, so we have one error on RGB matrix on line 11. It tells us that the syntax is not correct. So let's go to that one. If we read the source code, we see that there's a function here, and inside there's an inline function. I think in C++ it's valid, but in C it's definitely not valid. Searching again, this seems to be a GCC extension. Clang actually decided not to implement it. It's definitely not following any standard, so we'll have to rewrite that. luckily, I'm well prepared and I already have something ready to go. In fact, after inlining those two functions, there is less code and it's, in my opinion, more readable. So let's go with this. And at least it should be equivalent functionally. So let's rerun. Yeah, let me remove that warning. I don't know why this, come on. Going too fast for me. It's in underscore wait. No, underscore wait dot h. And not this one. Not this one either. Okay, let's see. Here in wait.c. Oh, a C inline inside a header file. That's nice. And this is the real message that we're seeing. So let me comment this out for now because it's not related to what we want to do. Anyway, here we have an actual error. Include next in file found relative to primary has include next. And if we look at the error message, the error is that include next absolute path on this file seems to be necessary. I'm not sure why include next should be supported. So let me go on the compile commands for timer.c and actually no, let me do it a little bit cleaner. Let me add the CPP extra options here for everyone. CPP extra args and enable this. Actually, it's an array. No include. And this should work better. At least we have a cleaner parsing now with much less warnings because I disabled the optimized warning. There's still two of them left. One that is actually shown in the real build. And now, okay, are we going to complete the parsing? Crossing fingers. You see, it's comparable. It's a little bit faster than actually building because the parsing doesn't try to optimize the code. It tries to create an internal representation of it. But anyway, since we're moving forward now. Oh, okay, another one. Syscalls. Okay, syscalls. In this particular case, the OS is very simple in its usage. There is no syscall, in fact. So we'll disable syscalls, and since I know this is also going to cause trouble, it's actually just using it in a particular way that it's doing direct calls to the OS. So there's no need for system calls. Let me do another parsing, and hopefully here we'll reach the end. See? Okay, well, we're at least starting the analysis now. The analysis was a little bit too short to my liking, but we started something. There's an out of bounds right. That this is a classic. So here what we have is that we're actually trying to do an access to a little bit of memory, which actually does not correspond to memory that exists. And that's actually voluntary because here it's a memory map register. So we're going to have to map the registers of the hardware for the DMA engine and some buffers and so on. Still, let's confirm this. I'd like to start it in the GUI. Can I? Yep, here. Inspect. I can start the root cause investigator. One and start it again. Anyway, since this is probably the trouble, here I'm going to open the stubs file, which is already prepared. and provide it as default, and then just add some commands that are some declarations that will be used. I'm not saving here because I keep here unsaved because I want to see how the root cause investigator will confirm, but I already prepared a number of areas here. Oh, and of course, I need to add the macro, which I forgot to copy. Attribute this address x area. But the reading is much better with hardware area instead of that long attribute. Anyway, let me open this in the root cause inspector. Here we can see the issue. The issue is, well, it's indeed some specific address CCR, which seems to have, if I show it in hexadecimal, some physical address which is arbitrary for us, but well defined in the STM32 chip. So this is indeed the memory mapping issue. So here we can just save this one. And now that we have this, we can start to inspect again, because now we expect that the parsing will lead to hopefully interesting issues. And we will start the root cause investigator each time. So it's going to parse again. Because we have a number of files here, it's parsing again to make sure that it is getting the total consistent set of variables and code. And each time we modify the code, we have to reparse. So it's taking a few seconds, but we're already almost at the end. Okay, and now it's going much, much further. Seems like it did something. Again, let's open in the browser. 737 undefined behavior. That's probably too much. Let's look, and usually the right thing to do is to look at the first one. Okay, index bound. Okay, well, let's see. The I and the N, the I is coming from here. You can see the value is coming from 8, and this is because the limit here is coming from here. And we see, however, that the register is containing something undefined. Maybe we want to initialize this counter to 0 because this is the initial value in the chip when the system boots. So now we need to do something a little more advanced. We need to actually introduce a new main here, and then initialize some areas of the code, some areas of the registers to 0. And we use this make unknown for this to set them to 0 and then let them go. And we want to change the entry point. Instead of it being main, we want to use my pre-main here. Up and the comma in the syntax. Okay, next round. Oh yeah, let me do something else. I wanted to remove this because this was not necessary in here, and we'll may add it in later on. Okay. Next round, almost done with the parsing. Now we're down to, I hope, less than 700. Okay, 700 undefined behaviors. But we still have this one, interesting. Okay, so maybe that wasn't the issue. What could be happening? Let's see. I want to enable this option, but I will do it directly in the compile commands, in the config file. Whole program option, is it there? No, I will enable it here. Graph Pro. I think that was the option, right? Whole dependency. All right, so that's the right option. Let me kill this one and run it again. Let's see if we get something better. Again, can close all the panels, and still our issue. Interesting. At least here I have now the alarm inspector, but I can see that I counter is 0. Therefore, N is here. What? I counter is 0, and N still becomes something strange. Okay, so looking at it, something strange here. Oh, that's the trick. So here, the I counter is cast to volatile, and in this particular case, the contents are over approximated, because when you read a volatile, then actually you don't read the specific value that was stored. You read any potential value, because the definition of volatile in C is that someone else may have modified the value, and in that case, with anything. So let's take a shortcut and just remove the volatile for now. And of course, the proper way would be to keep the volatiles, but solve them one by one, and either educate the specific read to be more robust in the code, or tell the analyzer that actually this is not really a volatile read and it can remain precise. Okay, next round. And let's see if without the volatiles we get further. This is even shorter. Is it better or worse? Okay, at least we don't have an issue here. For potential issues, what's happening here? So what's going on here? Well, I don't really understand what this alarm is coming from. So we have the alarm inspector available now that will give us some more explanation. So we can inspect the alarm, and on the left side here, it's giving a little more explanation. Well, at least I can look at the next, and I can see that this DLP next pointer before the alarms, before the verification here, is pointing to either the pointer to VTD list, whatever this is, or null plus anything, which is not a good sign. Normally pointer should point to something that we know. And in fact, after this alarm is done, then the root cause, the analyzer will reduce that to all the possible pointers, which is not necessarily what we want either, but at least here, this is wrong for sure. So, okay, contract that if we want, but not sure if this is going to be useful. And DLP is much simpler. So the problem is with that DLP next. Let's see. So it tells us that DLPH is coming from a D-list. Then that D-list is inside VTLP. I still don't understand what this is, but okay. And then VTLP was an initialized and set here. And if we go up the call stack, it seems like there was a call to a function port switch. And that port switch function is using function specification. So that means it's actually well, let's see. Function specification means there is no implementation for it that the analyzer knows about. Of course, in the real build, there is one, but in here, we can keep only the C source. So if we go to the definition, we see that the analyzer made some assumptions on what the code is because it doesn't have the code in reality. It only has the declaration that we see in the source here. Okay, well, let's confirm that. This is probably because we have some assembly function. So if we go and look in here, and this is sorted by tree, we see that there seems to be one, but that's not exactly the function. And there is another one, ARM v6, GCC, port switch. So that could be our stuff. And here, this is doing context switch between two threads. Okay, so that port switch is an assembly function. What do? We have to create a stub that is sufficiently mimicking the context switch, but in our case, we want to continue with the correct sequence with the same thread instead of switching the thread. So, well, let's do that and go to the stubs here and then create a new version of the function. All right, let me go back to here actually and copy the prototype. And here, okay, and make it an empty function to do nothing. Okay, try again. No, yeah, okay. I need to include h.h and probably for GBOS, and also say that we want to build this file because those types and this include path will be somewhere in the GBOS. I want to specify that the tstubs file is compiled like the file which we had trouble with. Okay, so this stubs. Let's see, will compile like let's see, GBOS. Red. Okay. Simple. Oh, even shorter. So what's the problem this time? 1 UB. Okay. This is another issue. So what do we have here? Bit. It can be F. And then bit times 2 means it can be, okay, let me switch back to integers. 30. 3 shifted by 30 means that we will actually go beyond the overflow, and it's the top bit is like we were going to shift it by 2. So indeed, here we have an issue. BU. Let's see, what is this file? It's harpal LLD, and we need to definitely we have a signed overflow. This is a real issue here. Let's solve this one. .c, which one was it? STM32. F4. Right, is that the right file? How? GPIOV3. Harpal LLD, that's the one. And here we have the problem at this point, and probably this one has the same problem, and just for good measure, I'm going to do it here. Okay, so this is definitely a bug because those invalid shifts could be optimized away by the compiler incorrectly. if it can detect that this can overflow. Usually the compilers will do the right thing, but definitely that invalid shift is a bug. All right. At least the good news is that the correction is quite easy as well. Just make it unsigned. Then the unsigned value can be shifted easily because it has 32 bits, and then the shift can go on. Okay, still another trouble. Okay, very quick one. I hope we can reach the point where things will go a little bit easier. SRC. So SRC is a null pointer. This is not good. What's going on here? Okay, let's try to inspect the alarm, and then we'll try to understand what's going on here. So we've gone through protocol init. We're still in the init phase. There is a check inside the EEPROM. The EEPROM is trying to read word, and at this point, the address is already 0, which is a little bit concerning. And so that means really we wanted to explicitly set it to 0. This is a conscious decision to put 0. And the problem is, let's read the algorithm. SRC here seems to be cast to UN32 for the comparison, and then it's a pointer, but each time it's used, there is a clean cast here. And destination is a real pointer. We see that we dereference it, but SRC is never dereferenced. And in fact, when we want to read a data word, it's cast to an integer type, which is a little bit strange. So let's see, let's go back to the source. What I suspect is that actually this driver, so this is an EEPROM. An EEPROM is typically memory, which you cannot access directly mapped in memory. You can only send a particular request to read a particular byte or set of bytes. And this is what we see here. It's calling a function, and if we go inside that function, EEPROM read data word, we go and we actually, the address is actually an offset here. It's not a pointer. So here we have something where we try to cast a pointer, but somehow it's used as an offset here, which is a little bit strange. So that SRC here means it's actually an offset. And somehow this address is also an offset. It's used as a pointer, but it's truly an offset. And if it was 0 as truly an integer, not a pointer, then doing this operation would be totally valid. We need to look into this a little bit more, but actually, if I go back in the particular file here and look at the interface, it seems like this is another real issue. Okay, so EEPROM STM32L4 here. Let's see. Problem was inside. Where? Come on. What was the line? Line 533. Okay. We have the problem here, and at SRC. Let's see if we can find the definition of this. Seems like many drivers exist for the read block, but all of them actually have the little strange behavior that they cast even arbitrary numbers into a void pointer. It seems like truly the interface is counterintuitive. It should be an integer. If everywhere, even in other drivers, the intention is to be an offset, then it should be an offset, not a pointer. So probably we need to change that code again to transform that address into a pointer here and then truly use it as a pointer. I mean, truly use it as an integer. All right, so let's see. Oh, and actually it's even worse. Here we have a const. No, it's pointer to const. So let's use it as just uint32. And then cast here to uint32 as well. Then we don't need that cast anymore. And then suddenly all of this can disappear and disappear. In fact, it should also be even casted to a uint16 because this was the real type cast. And not a pointer, just a real value. Okay, so in fact, there are less casts now. And the code is a little bit cleaner to read. Okay, so that's the second bug or third bug we found here. After some portability issues at the beginning, we found real issues. Really, the real, okay, what did I do? 526. Yes, of course. Need to do the post increment separately. No? No, that wasn't the problem. Just reading stuff. It's just a parenthesis issue, and in fact, we have the same parenthesis issue here. Okay, let's run it again. So at least it passed. All right. Yeah, I mean, this is a little bit strange, and I don't know why, if the intention was to address all EPROMs with an offset, why this was not an integer in the first place. This is probably something for improvement. But that's where, I mean, the QMK firmware in general is something done by a community, and well, we can't blame them too hard on those kind of designs. Still, that's something to improve. Okay, next one. Actually, we're still in the same function. No, another function. Before we were in read, now we are in write. And what do we see here? Well, we have the same kind of issue. Again, it's a pointer, and here we have that pointer magic, which is again 0. Okay, well, let's solve this one as well. uint32t, uint32t. Likewise, we don't need the cast anymore. Then blah, blah, blah. Here we don't need the cast anymore, and that means we don't need that cast either. It's simplifying the code a lot more. No cast needed. No cast needed. No cast needed. Is that everything? Yes. So this time it will be the last one of the run. I will just run like this and generate without opening the root cause inspector, and I will just let it run and then create a final report, as we've already found a few things, and it's time to create a final overview. All right, now it's finished. Then now I can generate the report and open it and see, okay, well, so we still have 14 alarms to investigate. The work is not done, of course, but this is interesting as we've found already a few issues, and I'm sure there are some left over here. We've reached also about 40%, almost 40% of the functions of the code, which is actually quite nice. Well, of course, again, more work will lead to a better coverage of the system here. All right. Kevin, over to you again. All right, so if we look at what we actually found during the analysis, we found two portability issues early on during the parsing. One about that thumb interworking, which is actually not necessary. Another one, which is a very strange construct, which is really a specific GCC extension. And again, that could be simplified very quickly. So, I mean, probably we could solve them, but they're not bugs. They're just syntax issues. Issues that could be bugs, and if you ask the compiler to optimize, this could go wrong. Is a signed overflow in that PAL LLD set group mode. Another one in the EEPROM, which really has a bad API. That API probably should be changed for all the architectures, but then that's a base work. Looking at the report in detail, which I obviously had done before the live session as well, there's one initialized access in processor RGB matrix, which is potential crash. It could happen, and I think I actually reached it once in the lighting of the LEDs of the keyboard. There's one invalid shift regarding the layers, the layer management. The layers is when you click on when you select control or function, these will move to different pieces of different mappings of the keyboard, and well, there's a risk that this could go wrong. The real killer is the last one here. There is the tool detected a deep recursion, which is not a straight recursion. It goes through multiple functions before moving on, which happens when you have nested actions. And you record macros. So if the macro is too deep, it may crash the keyboard. And there doesn't seem to be a protection somewhere in the code. So again, that needs to be investigated. But maybe if you hack too many complex macros, maybe you can crash the keyboard, which, well, is not fun. All right, but well, the good thing is in half an hour we found things. In the end, TrustInSoft Analyzer is really great to analyze that kind of code. It enables us to understand the code quickly, to analyze and find alarms, which are in the very vast majority of the cases actual real issues. That's what we saw here again. It can enable exhaustive static analysis if you give it sufficient effort to reach all the branches of your code. And again, that's formal verification. So once you have done this analysis, you have a guarantee that there is nothing left in your code if the tool does not give you, does not raise any alarm. And well, again, that wasn't the topic today, but you can integrate it into your pipeline, in your CI/CD. There, we've seen code coverage. We've done fault injection because it was kind of hardware fault injection at the same time. And it ensures that there's a consistent data and control flow analysis, because that's how the tool works.
Well, thank you, Roland. I know that was a good detailed overview of your favorite keyboard. So thank you for that. Just as next steps, as I'd mentioned earlier, this is available for online viewing and on-demand viewing. If you are interested in participating in any of our Code Unboxed events, where you're more than welcome to join the event and even work with us to have your respective code analyzed. Please do reach out and contact us at trustinsoft.com. And with that, thank you all for your time today. Have a good day.
Thank you.